Thank you for joining, everybody. We'll get started. Thank you for joining the LDES Council Technology Sharing Session. You'll hear from two member companies, MGA Thermal and 1414 Degrees. My name is Suman, and I'm the Program Director at the Long Duration Energy Storage Council, or LDES for short. And I'll just kick off with a few slides before I hand it over to our presenters. So we're seeing really a decade plus of record-breaking climate events, and we see more and more communities, companies, and governments around the world implementing net zero targets. And we recognize that to achieve these net zero targets, LDES will be crucial as a solution. LDES provides the flexibility, resiliency, reliability, and affordability. And the LDES Council, we have member companies who are really dedicated to developing and scaling LDES technologies and expanding the marketplace. And we're seeing more and more projects come online. We are expecting to see an exponential growth of LDES projects being announced and coming online in the next couple of years. So really exciting. And many of our member companies are a part of this, this acceleration of the technology. So we have the LDES Council consists of about 65 companies who represent 25 or almost 25 countries. We have technology providers and anchor members really representing the entire LDES ecosystem. And this is another way we have captured our LDES Council technology providers. We are technology neutral, and we recognize that there are many different LDES technologies and solutions out there for many different applications. So we have many members who are doing thermal, electrochemical, mechanical, and chemical. And today you'll hear from two Australian companies who are thermal energy storage solution, providing thermal energy storage solutions. And just to, before I hand it over to our speakers, please check out our website, ldescouncil.com. We have 4 reports that are publicly available, ranging from 24/7 PPAs to policy toolkit. We also have reports on net zero power and net zero heat. Please do follow us on our social media on LinkedIn and Twitter. We do share a lot of news and member updates through social media. So please do reach out to us and follow us on the social media. And I'll present our 2 speakers today who will be talking about their companies, their technologies and projects. Alex Post is the co-founder and CTO of MGA Thermal. We'll hear his presentation first. And Mahesh Venkataraman is the CTO of 1414 Degrees. So we'll hear from him second. Please use the chat function to pose any questions you have to the speakers. We'll ask the questions at the end of each presentation. So please keep the questions coming, and we'll have time for Q&A. So Alex, I'll hand it over to you first.
Sure, thanks, Suman. Is that presentation coming up okay?
Yep, looking good. Thank you.
Okay, thanks everyone for coming. Very keen to use the opportunity to share a bit of information about MGA. I'll cover a bit of background about our business and our core invention, as well as our technology, and then some of the exciting projects that we're working on at the moment. So we started off as a materials science research group within the University of Newcastle here in Australia. Our core invention was a composite material which was designed to be a purpose-built media for thermal energy storage. And really, we founded our company to commercialize and scale up that technology and to get it out into the real world, functioning as an energy storage medium. So very quickly, having a look at the company journey, the invention itself took place in 2011. After that, we had a period of material science research inside the university. So looking at different potential materials that we could combine to make our alloys, testing their properties and really working out how they worked and how best to use them. In 2019, we founded MGA Thermal. We secured that IP from the university and we spun the company out. Since then, we've received a couple of grants for incrementally larger scales of manufacture of our material. So we started off with very small samples produced in lab, talking sort of 30mm discs, which allowed us to demonstrate that the material worked, but it wasn't yet a commercial embodiment of the product. Then we created a pilot manufacturing line, which could make full-scale blocks of our material. So they're about 4 liters in size. In a very manually intensive process, we could make about 60 per day flat out. And it was quite exhausting work. So we very quickly moved on from there once we proved that out to a commercial scale manufacture, which is what we now do at our Tomago, New South Wales manufacturing facility. So that's using automated processes and continuous processes rather than manual and batch to produce commercial quantities of our material. The current scale of manufacturing that we're at is about 1 megawatt hour per day of our blocks. So how do the materials work? Well, at its heart, they're a composite material. We make them out of 2 different components. The first of those is a solid matrix material, which essentially forms the body of our blocks. Now, within that matrix, we have distributed grains of a phase change material, typically a metal, which in operation melts and freezes repeatedly, storing latent heat. And that's our primary energy storage mechanism. So the idea behind that is that we achieved the high energy density of the latent heat material without having the complexity of handling a material when it's a solid and a liquid. Macroscopically, they're always solid blocks because it's small individual discrete grains that are melting and freezing rather than the bulk of the material. So for the thermodynamicists amongst us, an enthalpy plot, just looking at the stored energy density, so kilowatt hours per cubic meter as a function of temperature, baselined against a couple of other media that are used to store thermal energy. You can see that we have the gradual increase in stored energy with temperature, which is sensible heat. And then we have these kick-ups, which are the latent heat occurring at a couple of different temperatures for different materials that we've developed. And really, there's a lot of science that goes into that for us. It's always a trade-off between how much PCM to include in our blocks without compromising their mechanical properties. Obviously, you want to have as much PCM in there as possible to increase your energy storage capacity, but you don't want to overdo it. So you need to maintain some sort of matrix structure. We prioritize the use of sustainable materials in our blocks. So these are materials that are potentially waste products from other industries, not only because they're typically low cost, but because they are sustainable. Our customers are particularly interested in decarbonizing their processes and hitting sustainability metrics. So having a product that has a low CO2 footprint is very, very important to them. So we're sort of continuously working to evaluate new materials, try them out in our own research labs, which are now in-house, and incorporate those into our products. So we do have quite a strong ongoing R&D focus within the company. We were lucky to inherit a lot of that from the university when we spun out. So we kind of maintain that going forwards. We're always looking at new materials to develop, especially as some sort of low carbon products hit the market, as other companies are working on their decarbonisation. So really the 6 key advantages that we believe this composite material has allowed us to achieve are a system that's renewable friendly. So I'll get into this in a little bit, but we can interface our material with solar energy, wind energy, waste heat from industrial processes, a number of sustainable sources of energy. We have a high capacity because of the utilization of that latent heat. Our material is economic because we're utilizing very prevalent materials and those that are waste feedstocks. So they're not expensive to make. The modularity allows us to stack them up into very large storage systems or to go down quite small very easily. Sustainability I've covered, and safety. It is an important issue to cover, especially with the use of phase change materials. Typically, if you have a very large volume encapsulated, then you risk rupture if there's any sort of failure of your encapsulation mechanism. interestingly, if you look at our product, if a brick is to fracture in operation, then you're not actually exposing a lot of molten material. You don't have a rupture. You expose, a small number of 1 millimeter sized grains. So it is inherently safe. So having a look at our manufacturing here in Tomago, that 2021 process was a manually intensive pilot production line. So we're now at the 1,000 block per day stage. Each of those blocks stores approximately a kilowatt hour of thermal energy. So that gives us about a megawatt hour per day of manufacturing capacity, which is enough for our current scale of projects, which are typically pilots and demonstrators. 2024, we're looking at bringing a manufacturing line doing, so 10,000 blocks per day, 10 megawatt hours. At 240 days per year of manufacture, that equates to 2.4 gigawatt hours per year of thermal storage capacity, and then continuing to scale up. So through 2026, 2028, eventually approaching 1 million blocks per day. So it is a large scale manufacturing operation. However, we're utilizing a lot of technology already used in similar industries, which is based around very large volumes of modular blocks. It turns out that humanity's been doing that for quite a long time. So with a bit of material science intervention, we've managed to repurpose a lot of those processes for our own use. So obviously a thermal storage block on its own isn't enough. You have to be able to offer all of the surrounding infrastructure to go with that to actually utilize it as a thermal storage material. Initially, we didn't have that when we spun our technology out. We were, I suppose you could say, of the naive opinion that you can just invent a new material and the world will figure out how to use it. Part of the scale up journey really is learning those hard lessons. And so we've, quite early on, we came to the realization that we did actually have to design the infrastructure to go around this and the complete solution, including the charging, the storage and discharge. So we now have that expertise we've managed to bring in-house, and we have the entire system developed around the complete charging, storage and discharge of our storage media. So we charge electrically. It's using simple resistive heating to put energy into our blocks. We heat them up through the phase change. We can also accept waste heat from industry if it's at an appropriate temperature. And we discharge using an inert gas loop, which can then be connected directly to an industrial process, or it can be used to generate steam for either industrial use or for power generation. Our core product utilizes aluminium as a phase change material, so 660 degrees Celsius melting temperature, which is very convenient for making steam for a range of industrial processes, but also for power generation. So onto the project side of things. We have a demonstrator project nearing completion. I don't know if you can see it, but it's actually outside my office window in the background. So we expect that to be beginning commissioning very, very shortly. It's been funded by the Australian federal government through ARENA, and also with the help of Shell through the Game Changer program. And really the goal of that pilot is to demonstrate the complete use of our technology. So even though we're conducting it in-house, it's essentially ready to be a commercial unit. It's charged up using 0.5 megawatt of electricity, which currently is over the grid, but will very shortly actually be coming from a rooftop solar system on the roof of our factory. It stores 5 megawatt hours of thermal energy, and then it discharges, in this case, to moderate temperature steam at 385 Celsius 40 bar. And we can discharge that at capacity for a 10-hour period. So that gives us our 5 megawatt hours of storage capacity. And that corresponds to about 3,700 of our blocks. So it's about 4 days of manufacture for us to populate this unit. So the use cases that we're really focused on are the industrial process heat and the retrofit of thermal power stations. So that's really the utilization of steam at temperatures up to 550, 600 degrees tie in very nicely with these two use cases. I probably won't delve into this in the interest of time, but we have recently completed a bit of a market study on a lot of the different industrial process heat uses out there. We believe that about 2/3 of the market is reliant on steam at temperatures up to about 600 degrees, and that includes power generation as well. So that is our core focus at the moment. We intend to target those use cases that need a very, very stable, long duration supply of steam, whether it's running a power station or powering an industrial process. All right, so pretty fast paced there, but that was the content that I had. So I hope everyone found it useful.
Great. Thanks, Alex. That's really fascinating. Any questions from the audience? If you have any questions, please use the Q&A function. I do have a couple of questions myself. What would it take to go from a demonstration unit to a more full-scale commercial use and application?
So we already have feasibility studies underway for a couple of commercial projects. They're at the larger scale, so 1 to 2 orders of magnitude larger than the pilot that we have nearing completion here on site. Really, the way that we're scaling our technology up is 2 large-scale systems. So we're not necessarily duplicating systems of this size. We're scaling things up in all dimensions. So a larger TES enclosure, a larger heat transfer loop, larger heat exchangers to start to benefit from those economies of scale. And to really buy into the modularity of the system. So all of the core principles are demonstrated by this. We're basically just increasing the size of all of our components.
Great. And we have a question from the audience. Is there any sintering or loss of surface area of the AI particles during the thermal cycling?
So we do have quite an extensive material science lab on site. We're constantly sort of going through thermal cycling, testing for those kind of things. And if we select the right operating temperature, then no, we don't see that. So good question.
Do you see?
I should probably add though, we're not reliant on sintering of the particles to form our blocks. It's the inert encapsulating matrix that gives it its structure and holds it together.
Do you see any opportunity to retrofit coal-fired power stations with this technology?
Yeah, absolutely. So the feasibility studies that we're currently doing are, well, one of them is for a gas-fired power station, but in terms of the process steps, it's very, very similar. So we're looking at the replacement of the boiler, and everything downstream of that is using pre-existing infrastructure.
Another question, what is efficiency of energy storage through MJ Thermal?
So our charging efficiency is very high because we're using simple resistive heating. It's approaching 98% on the charging side. And discharging side, our only loss mechanism besides thermal radiation from the outsides of the container is a circulation fan, which drives our gas loop. Now, of the energy that circulation fan puts into the system, a lot of it actually goes back into the heat transfer fluid. So on the discharge side, we're approaching 95%, which means round trip, we're at about 93%. In terms of thermal losses, it can be optimized depending on the thickness of your insulation layer. We've built our system around a target of 2% per day for large scale systems, which means you can store for several days up to a week without significant loss. But really, if you're chasing a very long duration application where you need to store for several weeks at a time, it just means an increased capital cost on insulation.
Got it. Great. Is MGM offering any pilot currently? I know you talked about the demonstration unit and feasibility studies. So are there other pilot studies that pilots you're looking at? And maybe also give a timeline on when you anticipate to have results from those, the demonstration unit and the feasibility studies?
Yeah, absolutely. So because we have ARENA funding for this pilot, part of that is quite a public knowledge sharing process. So we're forming what we call a SRG, or a stakeholder reference group, which is basically a group of industries that are interested in the performance of the pilot. So that's underway. The initial group's already been formed, but we're still accepting members. So reach out if you want to be a part of it. And really the core objectives of that group are sharing the outcomes of the pilot. So all of the in-depth performance metrics, as well as giving us specific targeted use cases to run through the pilot. So if you have your own industrial process that you're interested in seeing piloted through this, we believe that we can, to a large extent, probably run that through our own pilot rather than doing a new pilot for every single situation, and demonstrate that use case. But once this is complete, we're then looking at the next scale of larger pilots. So very interested if anyone wants to approach us about those customer-led pilots.
Yeah, we have a couple more questions. Do you anticipate degradation of the material over time, and what would be the expected lifetime?
So we're targeting a usable lifetime of the material of 30 years. So we don't expect it to be a replaceable commodity material. It's meant to be an initial investment, and then it runs for the life of the plant. Obviously, testing something out for 30 years is quite difficult in a rapid testing environment. So we're driving the material through quite rigorous thermal cycles at the moment, where we essentially hit our material up over a 15-minute period, and then quench it down to atmosphere and drive it through those thermal cycles very aggressively, to kind of try and simulate the effects of any thermal stresses that could degrade the material. We also do temperature holds at a range of different temperatures to try and define upper limits on operating temperature before we see any degradation or that sort of thing. So obviously it is a key concern for thermal storage material. It has to be able to survive in its operating environment for a long time, unless you want to replace your entire TES media throughout the project. But we expect it to be a long-lived component.
Okay. Have you ever installed anything like this in a cement plant?
We haven't currently. So the upper limit on the operating temperature of this is 700 degrees. And I believe that some of the temperatures required for cement are a bit higher than that. So it's something that we may sort of delve into further down the track, but it'll need development of new customized materials for that application.
Yeah, and we have a couple of questions about the cost. Could you provide any insight into the cost of your system?
Yep. So as a very rough guideline, we fall sort of in the median range of the cost benchmarks that LGS Council released last year. So I think people can look those up in the report. Because we're utilizing readily available materials, so everything that we make our blocks out of is in the top 25 most abundant materials on the Earth's crust. So we pretty quickly went through and ruled out anything that was, prohibitively expensive or dangerous or resulted in a high capital cost. So it is, it's a relatively cheap material, even though it's custom made for this niche application.
Yeah, and we'll take one more question. What heat transfer fluid is used to discharge?
We can use a range of different fluids if we want. The fluid that we're using in this pilot is nitrogen, just because it's quite cheap to generate on site, and it's inert. We can use CO2, argon, a range of different fluids. Okay, great. Thanks, Alex. Feel free to continue to type your questions. I know we have a lot of questions coming from the audience. Alex, if there's a type answer. If there's anything you'd like to answer using the Q&A function, please, we can do that. And we can move on to Mahesh's presentation. Thank you.
Thanks very much, Sumin. Can you see the slides?
Yes, we can see the slides.
Thank you. First of all, good afternoon, good morning, good night, wherever you are in the world. The beauty of these online seminars is that gives you the flexibility to attend seminars across the world and whatnot. I can see some of the audience members over here were part of the rapid fire technology sharing round we did a couple of months ago. So this forum will give me an opportunity to explain what our technology does in a bit more detail, why we do what we do, and how we do it as well. So to start off, a lot of the things that Alex mentioned in his presentation and Suman before that are very applicable to everyone in the thermal storage space right now. But I want to highlight a few key things over here. So when we talk about long duration energy storage, the discussion more often than not is around the electricity storage aspect of it and resupplying the electricity. But industrial heat is one of the holy grail of the decarbonization puzzle. And as you can see from the chart on the left, about 60% of the emissions from the industry actually comes from the fuels being used for heat. And these can be split into the low, medium, high temperature range. And the high temperature range, especially above 600 degrees or so, is where the fossil fuel usage is very, very predominant. In fact, the net zero heat report, which the LDS Council did a few months ago, will show that about 90% of the heat at those temperatures, it's all coming from fossil fuels. And I have a couple of examples over here: alumina, cement, and iron and steel, which Alex did mention in his presentation briefly. The total energy cost for heat-related usage in these industries is about $400 billion. And just the iron and steel and cement account for about 55% of the CO2 emissions from all the industries combined. So these are very hard to decarbonize sectors, and that is one of the core focuses of 14D's thermal storage technology. So if I were to go and devise an alternative, a green heat alternative for these industries, what are the criteria that I might look at? And very, very high level, you want this to be a modular, scalable technology, which can go up to a gigawatt hour scale. I mean, a typical alumina or cement plant, you're looking at tens of megawatts per reactor in terms of the heat supply. So you need a very, very large storage to be able to cater to these industries. And then secondly, you want the ultra high temperature capability. Now, Alex mentioned that about 50–60% of these industries use the heat at lower temperatures, but then there's also a lot of alternatives at those temperatures. So for very low temperatures, you go with a heat heat pump sort of a solution. For medium temperature range, there's many sensible storage options. But when it comes to the ultra high temperature space, there aren't many alternatives out there, even in the thermal storage arena. And apart from that, you also want to have robust 24/7 operation, which is sort of a very important point for these industrial operations. They like to run 24/7 industrial reactors. They do not like to go cold once they're hot. So maintaining the temperature profiles, the temperature gradients in there 24/7, that's a very key requirement for their operation. The other opportunity there is the hydrogen, and which gets talked about a lot. Now, hydrogen, if you are using it for providing just heat, it gives you a lot of options in terms of storage of hydrogen and very, very long duration storage like seasonal storage and the likes. But if it is going to be on a daily cycling basis, the efficiency of hydrogen production and use for heat provision is actually quite low, and it is very expensive currently as well. So those were the criteria which we thought we need to address when we design our thermal storage solution. And that's where the hero of today's story comes into the picture, this 14D brick. Unfortunately, I don't have a name for this yet. We haven't named the brick. We have a social media competition going on for naming the brick. I'm personally in favor of Bricky McFick brick face. And this 14D brick is our building block for our thermal storage technology. So how does it store the heat is a very important question. And Alex did mention the challenges in terms of the material science aspect of it. Now, there's three variables in here. One is the phase change material, which we use inside the brick. It is a silicon-based alloy. Then you have the matrix material, and then you have the environment in which this is operating, could be air, combustion environment, etc. And you have to minimize the interaction or eliminate the interaction between all three of these. So the containment shouldn't be reacting with the metal shouldn't be exposed to the atmosphere, and the atmosphere shouldn't be damaging the containment material itself. So we've managed to solve all of those things in this 14D brick, which is in a form factor which can be mass produced and can be manufactured in existing facilities around the world. Now, the metal that we use is a silicon-based alloy. Silicon is one of the highest energy density in terms of its latent capacity, right? The only other element you would think of is boron, but using boron is very, very hard in this context. So what we've done is we've added some herbs and spices to the pure silicon, and that's what the Cyborg storage media looks like in terms of its energy storage profile. This plot is inverted compared to what Alex had shown earlier. So you can see the latent band over here, which extends over a fairly large energy landscape. And because we've been able to design the Cyborg storage media in such a way that can store very high energy density, this has impact on how big the storage needs to be. If you can store more energy into the box, or the energy density is very high, it means that your box is smaller and you can have lower thermal losses despite operating at very, very high temperatures. So just to give you an idea of scale, up here I have a Cyborg's storage media compared to a sensible storage media of equivalent temperature outlet, etc., and it will be about 2 to 3 times lower. More quantitatively, if you compare it with other phase change and sensible storage material alternatives, so like steel or oxide-based material like silica or alumina, the conventional nitrate-based molten salts, graphite, and aluminium. So you can see that the Cybrick or the 14D brick can actually store a lot more energy, up to 2 to 3 times compared to some of the alternatives. Now, the red shaded portion over here is the latent phase. So about 60 to 65% of our energy actually comes from the melting and solidification of the metal, and the remainder is due to the temperature swing in the storage block itself. Now, where can this brick be used is there are multiple configurations you can use this brick in. The most simplest one would be as a hot gas generator. You can stack these bricks up in a certain arrangement, heat them up using resistive heating elements, and then use some heat transfer fluid to extract that energy out when it is needed. And that is this configuration that we've built in our workshop here in the demonstration module. I'll talk about that a bit more later on. But the hot gas generator can act as a replacement for natural gas in a lot of the high temperature industries like alumina and cement. And there were some questions in the chat around the cement and alumina industry as well. So the phase change material we currently use melts at about 1100 degrees or so. So you can go up to 1000 degrees in terms of the outlet temperature from the demonstration module. The next generation electric reactors is another opportunity. So a lot of these industries are looking to electrify their operation with the assumption that in very near future, a lot of the large portion of the electrical grid will be decarbonized, and converting to electrical reactors can reduce the carbon footprint of their products. So having a high energy dense material directly integrated with the reactor gives you that opportunity to design electric reactors which have inbuilt storage in there. You can also use these bricks directly into waste heat utilization. So for some of the industries like glass, where you have regenerative furnaces, and there is fuel port switching every few minutes or so. One of the key constraints for these furnaces is to maintain a constant temperature profile inside the furnace, and having a phase change material in there at a very high temperature would give you that opportunity to minimize those fluctuations. So, talking about a bit more about the demonstration module, which we are currently commissioning. The construction was completed about a month ago or so, and we're undergoing commissioning right now, doing the fine-tuning stuff. And it's a very simple configuration, as I mentioned earlier. So you have electrical resistance heaters in there, which can convert the energy from renewable sources and store it as heat in the bricks. And then there is a heat transfer loop inside, which basically captures that energy and supplies it to a process 24/7. This CyBox demonstration module is at a 1 MWh scale, and it's a modular design. So what we're aiming to do is to demonstrate the performance at a 1 module scale, and then that can be replicated in larger builds. So the testing and experimental data from this will validate all of our engineering design models and help us scale up the CyBox technology for multi-module units in the future. A key feature which distinguishes our storage system from a lot of the others is around the capability to do a simultaneous charge and discharge in the system. By virtue of storing heat at very high temperatures, what you can do is you can have a fixed temperature outlet at a constant power rate from the box. And that's something that we want to demonstrate through our module as well. Now, coming back to the simultaneous charge-discharge capability, if your system or the customer demand requirement is for a 16-hour heat system or 24-hour constant heat supply, you don't need to design your storage with 18, 16, or 20 hours of storage. It really depends on what the generation profile is and what is the price fluctuation if it is grid connected. So if you have these curves I've shown over here are for an 8-hour discharge system, and it can charge in 4 hours, and it can supply heat for 16 hours in this case, and 24 hours in the case on the right-hand side, based on changing the charging profile of the system. This is run through an annual simulation, and something that we will also demonstrate using our module. And what makes it possible is that capability to simultaneously charge and discharge the system. Now, in terms of the application, we've been in discussions with a lot of these end users on understanding their actual process requirements. I mean, from a very static flow sheet perspective, it is quite easy to integrate, but there are actual practical challenges in these plant integrations, and that's what we're trying to solve in conjunction with some of these industries directly. So the alumina case is around two different heat needs. One is for the Bayes calcination process, where you need to provide heat to the main furnace at about 950 to 1,000 degrees, or maintain the furnace temperature at 950 to 1,000 degrees Celsius. So the opportunity for CyBox to integrate in such a process comes from air preheating, and also for preheating some of their feedstock, which is gibbsite. When it goes into the main furnace, it is already hot instead of what they use currently. This has multiple advantages, not just in terms of reducing the fuel rate in the calciners, but also in terms of increasing the productivity of the plant as such. And the second use case is around steam raising in these. Now, steam raising, that is not specific to aluminum industry. You could use that for power plants as well. And the key advantage over here that our system has is our discharge temperature is actually quite high, and you could use the existing infrastructure, the boilers which are designed for coal or natural gas firing, and still be able to maintain the temperature profile that you were getting with your fossil fuels. And it'll be a direct replacement for those fossils into the steam raising circuit. And What we found using our analysis is that we can replace up to 35% of the fossil fuels going into the calciners and up to 100% in the steam circuit. And this can reduce the CO2 footprint of alumina production by up to 70%. In fact, University of Adelaide, who are part of the Hill CRC, have done this analysis independently as well, and they've come up with even higher numbers for the fossil fuel replacement in the calciner using thermal storage at high enough temperatures. The other industry that we're targeting is cement production. Again, a very high temperature industry where roughly about 20 to 30% of their CO2 emissions is fuel related. Remaining is process emission, which comes from the calcining of the carbonates. So in this process as well, you can integrate a sidebox in a retrofit configuration and decrease the fuel rate by up to 8%, and hence also reduce the CO2 and the NOx emissions from these the calciners. Another interesting feature over here is that when you reduce that NOx emission intensity, the ammonia uses, etc., for catalytically disrupting the NOx emission also goes down. So it has operational advantages to integrating with the thermal storage. Now, in terms of the cost of the system, what I've plotted over here is the orange bars over here show the cost of electricity if you were using a direct electrification option. So that is, you could use an air heater or something of that sort to generate hot air continuously just by using grid electricity without any storage. This doesn't include any capital cost or anything. These are just the cost of the electricity from the grid. When you compare that to a sidebox-based system, the bar in the blue shows the electricity cost, and the green and the yellow ones are the capex and the opex costs for the system. And I've plotted over here a few different scenarios. NEM is National Electricity Market, which is the east coast of Australia, the grid, and grid prices for 5 years from 2016 to 2020, and a couple of synthetic data sets. And in all cases, you can see that you can reduce the levelized cost of heat just on a comparing with the energy cost basis by up to 15 to 20% in all of these cases. Another interesting thing is that with the recent increase in the fossil fuel prices globally, the cost of natural gas is so high that the sidebox can actually be competitive much earlier than anticipated. In fact, in certain countries, including Japan, Europe, and UK, the current price of sidebox is actually lower than what the natural gas prices would be. But as we all know, cost is just one incentive. These gas supply constraints are likely to continue in the future from an energy security purposes and also emissions reductions purposes. This is what will drive the change and a switch towards thermal storage sort of system. In terms of our pathway for commercialization, that has been our journey over the last few years. So the original test system, fairly high cost, and over the last 3 years, what we've done is we've designed a new storage media. We've updated the internal arrangement, understood the constraints around the heat transfer, etc., much better. We've done the insulation design, etc. So here is our current cost, and in future we want to be able to much below this natural gas as fuel price. This price was from 2 years ago, so natural gas prices currently would be much higher than that, even in Australia. So cost reduction pathway for us is based on continual R&D. We keep working on new materials every day. We have a separate stream of R&D looking at different temperature phase change materials, which are compatible with our storage concept, specially tailored for different industries, and then standardizing the module design and the technology scale up, which provides a smooth pathway for building larger units. Over the last year, we've also been working with one of the largest European refractory manufacturer for scaling up our technology. So initially, our products were using a casting method, which was a lot more manual intensive, labor intensive. And over the last 12 months, we've changed that recipe and made it compatible with a press product, which, I mean, about 1 trillion or so bricks are made every year, and these are refractory bricks. And the technology to make these bricks has existed for over 100 years, a lot more than that, in fact. So the pathway for scale up for us, because of this, becomes much more easier compared to a lot of the other proprietary manufacturing methods. And we're anticipating plant trials with these new recipes in the near future. So that's my last slide. In the last 3-4 years, we worked on doing the brick development, which is the core of our technology. Last year, we built this module, and the module was completed January 2023. This year will be dedicated in terms of the testing of this demonstration module. And in the next years, we will be trying to scale up to a commercial pilot and gigawatt-hour systems in the next two years' time. Thank you very much.
Thanks, Mahesh, for that great presentation. Same as before, if you have any questions, please feel free to chat them using the Q&A function. We'll take the remaining couple of minutes to ask any questions you may have. Mahesh, I can start off with a couple of questions. So in terms of a commercialization plan, are you looking at the Australian market, or are you looking at other markets as well?
A lot of our work so far has been focused on the Australian market, but from the beginning of this year, we've been in touch with global end users as well, and trying to do a plant assessment for those companies and see how the Cyborgs fits in their operations.
Okay, great. And the efficiency for your system, the round trip efficiency for your system?
Well, it depends on the size. Like Alex also mentioned earlier, for larger scale systems, you can expect roughly around 94-95% efficiency. The electrical losses are basically just the copper loss to get the power into the box, right? That's about 2% or 3% or so. And apart from that, the higher your energy density is, the smaller the box you can build, and that's where having a very high energy density helps. And the shell losses will be, I mean, regardless of what temperature you're operating on the inside, you can reasonably get around 60 to 70 degrees on the outside of the box. And if you do an intelligent box design, you're looking at a few percentage points per day of losses from the shell. And similar to the MGA system, the only other parasitic load in our system is the fan, which is driving the heat transfer fluid in the system, and that's during the discharge cycle.
Okay. We have a question. Can bottom ash of thermal power plant be used as side box for thermal energy storage?
Bottom ash of thermal power plant be used as side box. If I understand the question correctly, Amrish is asking whether this bottom ash can be used as a storage material. If that is the question, then, I mean, yes, that bottom ash contains a lot of inorganics and can be used technically for any storage material. But one thing to remember with the storage materials is that it's not just about the heat capacity, it's also the thermal conductivity, how quickly you can get the heat in, how quickly you can extract that heat out. That has a lot of system level advantages. So one of the key things that have worked in, that we've tried to include in our brick design is having a very high thermal conductivity. And that's where a lot of manufacturing processes also go, how to reduce the porosity or optimize the particle sizes and so on and so forth.
Okay, a couple more questions. What is the heat transfer fluid for the discharge?
We're using air as a heat transfer fluid in our current system. We've done testing with even high sulfur combustion products, so biogas and natural gas based combustion product. We have tested our storage media with those without any degradation.
And what is the TRL level for your technology?
I would say currently we are about TRL 6 or so. With the demonstration module, we want to move up to about 7 and quickly scale up beyond that.
Okay, great. Well, thanks for the great questions, and we'll wrap up the session today. I thank our two speakers, Alex and Mahesh, for a great presentation and great Q&A. Just for the audience, thanks for joining. We do have the technology sharing sessions every month, so stay tuned. We'll have another one towards the end of May, so we'll be announcing that shortly. But thanks so much for joining, and thanks again to Alex and Mahesh. And we'll follow up and share the slide deck and contact information of the speakers.
Thank you.
Thank you.
Thanks, Yuman.